this neutron, and again thinking in terms of plus and minus, and it gets the minus part knocked out of it, and it becomes just plus. So by doing that, I've changed this neutron with a plus and a minus into just a plus. I've made it into a proton. So this little negative electron that goes zipping out is just a minus particle. It's an electron now. And I end up here with an atomic mass number that really hasn't changed much. I've just changed a neutron into a proton, not too much of a change. And I have changed the atomic number by 1, haven't I? I've just essentially added a proton to it. Okay, I take this electron that I just made here, this beta particle, and it goes zipping off and bangs into another nucleus. And now it takes a proton, and it's kind of doing just the opposite of what we just did. Instead of making a neutron break apart into a proton, now this negative is banging into a proton, combining with it, and turning a proton into a neutron. And just the opposite thing. And now I've made the atomic number 1 fewer. I've effectively removed a proton. I made it into a neutron. And atomic mass number hasn't changed a whole lot with just a proton-neutron switch. So 3 different ways I can break down this material, and that's going to make a difference in what I end up with. It's going to change into different elements, or it might be the same element with just a different mass number. Okay, so true or false? Alpha particles are composed of 2 protons and 2 neutrons, which is essentially helium. One second. True. Yes, absolutely. Okay, so this means I'm going to change this material into something 2 atomic numbers lower. Right? I'm getting rid of 2 protons. So if I look at uranium-238, and the 238 is essentially the atomic number, and it's unstable. It's going to decay by a series of these alpha and beta emissions. And as it does that, the atomic mass and the atomic numbers are going to change. And I'm going to go through a series of changes into sometimes the same material, sometimes different materials, as I seek a level where the atoms are going to be stable. So I start at U-238. I have some alpha emission. I immediately go to thorium-234. That decays by some beta emissions, so it's still going to be uranium again. And we continue through a whole series, and eventually I get to lead-206. So notice I've gone from uranium-238 to lead-206 before stability sets in. Each one of those, a decay to a different isotope, sometimes a different atom entirely. And each of those decays happens at a set rate. So we can look at these materials and figure out how fast each one of these reactions takes place. And they've measured these things in labs, and they keep remeasuring things with more accuracy, more decimal points, better instrumentation. And there is a book about that thick that is all the decay constants for various elements. So we have a pretty good handle on this process. So we use these isotopes and these known decay rates now to help us age date rocks. And depending on what bracket of ages we want to age date with use different combinations of materials. For instance, uranium-238 to lead-206 that we just looked at, it has a half-life value to go through that whole chain of 4.5 billion years. Hey, does that sound familiar? What a handy deal to go. It goes right back to the beginnings of our solar system. Uranium-235 to lead-207, no, it only goes for 713 million years. So if we want to look at things more in that bracket, we'll use that ratio. You know, if you have a big bracket, a little bit of error isn't so bad. But if you have a small bracket, a little bit of error is relatively a lot bigger. So you have to kind of match the technique to the age you're looking for. And oftentimes we'll use more than one technique just to make sure we're getting similar results from different things, that something didn't uniquely happen to change the rate of one of those elements. Potassium-40 to argon-40 is 1.3 billion years, and that is a good one to use for a lot of things. This is the half-life. What do I mean by the half-life? That's how we measure the decay rate in these isotopes. A half-life means that's the amount of time it takes for half of the material I start with to decay into the material I'm going to end up with. Okay. The stuff I start with we call the parent material. The stuff we end up with is the daughter material. Why it isn't the son material, I don't know. But we go from daughter material, or from parent material to daughter material. And after half of that has decayed, so I'm half parent, half daughter, that's one half-life. I've decayed half the material. The second half-life means I'm going to take that half of parent material that's left and I'm going to decay half of it. So the second half-life now, I end up with 3/4 of daughter and 1/4 parent. I start with 1/4 parent now, I decay half of it. I'm going to end up with 7/8 daughter, 1/8 parent. Half of a half of a half of a half. Notice I never get to 0. Getting real small, but it never gets to 0. So that's how we measure the lifespan of these things. So, how much of the original material will remain as parent material after 3 half-lives? Give me 20 seconds. Half of a half of a half. See. And it's an 8. Exactly. You guys are way too good. Okay, so that's exactly what we see. First half gets us down to a half, second half to a quarter, third half to an 1/8. So when you get the news from the lab, they don't give you half-lives. What they do is they give you the ratios. So here, after the parent has decayed, we have half parent and half daughter, and in that case, it's going to be a ratio of 1. They divide out, right? Second half-life, I'm going to have 1/4 parent, A, and 3/4 daughter, B. That's 3/1, 3. That's my ratio of 2 half-lives. At 3 half-lives, it's an 8 parent, 7/8 daughter, so that divides out to 7. So those are the numbers that I'd get. So at 4, I'd have a ratio of 15, and at 5, a ratio of 31. So those are the numbers that you would see from the lab. and you can start getting an idea of the ages. Remember, we measured the decay rate, so we know what that rate is for each of these different elements, and it stays the same. It doesn't vary, it doesn't speed up and slow down. It's constant. So we know when we see these ratios how much daughter there is, how much parent there is. We can click it into these curves. We can figure out how many half-lives. Each half-life takes X number of years to happen. Bingo. Subtract that from the day and you've got how old the rock is. Pretty neat. But it's only really been since about the early 1950s that we've understood this well enough to apply it to rocks with any kind of accuracy and confidence. Now, you might think it's simple, but there's some issues. Okay, the ratio of parent to daughter material in an isotope after 3 half-lives would be. I'm not asking what the fractions are. I'm asking you to divide that out and give me the ratio. Split there between B and C. Okay. 1 half-life, it's going to be 1. 2 half-lives, it's going to be 3. 3 half-lives, it's going to be 7. Okay? Everybody see that? Check it out. It takes a little going over, but that's what we are. We'll pick it up here on Tuesday and talk about some of the problems we're doing.